for the do now, again, this was tying in units 1 and 5. So PES was topic 1.6, and then parts B and C are asking about rate constant and time to go from one out to another. And so B and C are both kinetics questions. So for this do now, if we look at the scoring guidelines, so I'll show you how College Board actually scored this question. This was a short question. This was worth 4 points. This was actually on the 2018 test. So for this free response question, part A said identify the element. Well, the element is nitrogen. That was 1 point. If we take a look at how we know that it's nitrogen, remember with PES, look for where the energy is the greatest. Look for where energy is the greatest. And so in the case of this PES spectrum, it's greatest on the left-hand side. Where the energy is greatest, those are the electrons closest to the nucleus. So those are your 1s electrons. Because we see other peaks to the right, that means that the 1s is filled. So that means that at 40 megajoules per mole, there are 2 electrons. So each line actually does represent 1 electron, but that's not always the case. So that means that we have 1s2 at 40, and then we move over. The next sublevel that fills is 2s. So there's 2s2, and then 2p1, 2, 3. So 1s2, 2s2, 2p3, PES tells us the electron configuration, which is why the element is nitrogen, because nitrogen has an electron configuration of 1s2, 2s2, 2p3. So that was 1 point just for saying that it's nitrogen. And then part B says calculate the value of the rate constant K. Now the important thing here is the fact that it says that it's radioactive decay. Radioactive decay is a common example of a first order process. So if something says that it's radioactive decay, that's another way to know that it's first order. Now remember, the only equation that you have on the equation sheet that deals with rate constant and half-life is T1 half equals 0.693 over K. Well, if we manipulate the equation to solve for K, K is 0.693 over T1 half. We know that T1 half, the half-life is 10 minutes because they tell us that. So 0.693 divided by 10 minutes. Be careful with units. 0.693 is just a number. Minutes is on the bottom. So you're going to actually have, when you solve, 0.069, or if you left it as 0.0693, that's okay. It doesn't say anything about sig figs. 0.069 per minute, or 1 over minute, because minutes is on the bottom. Per minute is different than minutes, so be careful with your units. That was actually 2 points. When it says include units with your answer, many times you either get a separate point for units, or if you don't include the units, you don't get the point. And so it was 2 points, 1 point for the correct numeric value and 1 point for the correct unit. And then finally, part C. If 64 atoms of the radioactive isotope are originally present in a sample, what is the expected amount of time that will pass until only 1 atom of the isotope remains? So how you arrived at your answer. So with this, I actually probably would have done this top method. If I were solving this, so in 2018, once I got the free response questions, I always work through all the FRQs. I actually solved it the way that they solved it up here at the top. Every arrow represents a half-life. And so what this top method is showing is what happens after every half-life. Remember, a half-life is the time it takes to get to half of the original. So I started at 64 and I went half of that, half of that, half of that, all the way down to 1. So 64 to 32, that's 1 half-life. 32 to 16. If you count those arrows, that's how many half-lives were needed. There are 6 arrows, so there were 6 half-lives required. 6 times 10 minutes is 60 minutes. But you needed to show work. So notice it says correct answer and a valid method. Now, if instead of doing this top method, you could have used the integrated rate law. Remember, the integrated rate law compares concentration to time. So technically, we have concentration. We have 64 atoms initially. We get down to 1 atom. We can plug that in for concentration. And we know the half-life, and the rate constant, right? We know K, because we just solved for that in B. We use ln. We use the natural log integrated rate law because this is a first order process. Radioactive decay is first order. And so doing this exact same thing and solving for T, we get 60 minutes. So either one of those methods work. So the way they scored this, remember, short questions are worth 4 points. So this was an entire short question. So general overview. This has 14 topics. Topic 14, we're actually going to talk about with Unit 9 because it ties in delta G. But you'll notice 7.1 to topic 10, that's all general equilibrium information. Topic 11 through 13 is KSP. So we did KSP when we did buffers titrations. They throw KSP into general equilibrium. So as we go through and we look at different topics of equilibrium, topic 1 is just an intro to equilibrium. So as we think about equilibrium, a lot of processes that we observe are reversible. Evaporation and condensation, so phase changes, are reversible. Dissolution and precipitation of a salt. So if I dissolve NaCl in water, and then I boil off the water and get the salt back, that's also reversible. We've seen acid-base reactions, transferring a proton as reversible. Redox reactions can be reversible. So a lot of processes are reversible, meaning that we can have a forward reaction occurring and a reverse reaction occurring. Systems that have reached the forward and reverse reaction rates being equal have reached equilibrium. So when something has reached equilibrium, the forward and reverse reactions are constant and equal. Equilibrium is a dynamic process. The reaction does not stop. I put that in capital letters here, bolded. Although we do not see changes, we don't see any changes occurring, that doesn't mean the reaction stops. The reaction keeps going, but there's just no net change. Reactants are converting to products at the same rate that products are converting to reactants. So we reach equilibrium. We can see it graphically. We reach equilibrium once the concentrations plateau. The concentrations do not have to be equal. The rates have to be equal. So the rates of reaction are equal once we hit equilibrium. So going along with topic 1, this essentially is just paraphrasing what was on the slide before. Once equilibrium is reached, we have reactants and products present at the same time. Concentrations or pressures remain constant. We see it again here. Concentrations remain constant once we hit equilibrium. Equilibrium is dynamic. The rates are equal, so we don't see any observable change. We can look at the equilibrium constant K, which we will look at much more in a couple topics later. But the biggest thing is if you're given a graph, can you identify when equilibrium has been reached? We'll look at particle diagrams. Can we tell when equilibrium has been reached? So equilibrium is reached once the concentrations remain constant. They do not have to be equal. Topic 2 looks at the direction of reversible reactions. And the biggest thing with this is this third bullet point, which is actually in the unit guide. When we think about equilibrium, we've looked at kinetics now. So yesterday we looked at kinetics. Kinetics focuses on the rate of reaction. Kinetics focuses on the rate. Equilibrium focuses on how the reaction progresses. Do we have more reactants or do we have more products? That is what equilibrium focuses on. If the rate of the forward reaction, so we have this reaction, let's say we just have reactants going to products, and it's reversible, so we have the double arrow. If the forward reaction rate is greater, that means that reactants converting to products is greater than products converting back to reactants. That means we expect to see more products being formed because the rate is greater for the reactants going to products. If the rate of the reverse reaction is greater, so that means that products turning into reactants is greater than reactants turning into products, then we would expect to see more reactants being created. Equilibrium is reached once the rates are equal. So we don't see more reactants or more products being formed. They're forming at the same rate. You can see another graph down here. We had equilibrium. So we had 3 substances at equilibrium. We added hydrogen. So notice how there was a spike in hydrogen. And then what happens is they eventually reestablish equilibrium. And the amounts are different than the initial equilibrium. But we know it reaches equilibrium when they remain constant. They do not have to be equal. They just have to be constant. So topic 3 looks at Q versus K. So this is only the first part of Q versus K, and this is actually focusing more on calculating Q versus K. K is the equilibrium constant. Could be Kc, Kp, Ksp, Ka, Kb, Keq. So K is an equilibrium constant. Make sure that you recognize the difference between capital K and lowercase k. Because capital K is the equilibrium constant. Lowercase k was the rate constant. So the equilibrium constant represents the amounts of products to reactants at equilibrium. So remember to calculate K, here it is, products over reactants. To calculate K, it's products over reactants. Q is called the reaction quotient. Q describes products compared to reactants at any point. Q is, oh, they give us values. Let's plug it in. That's Q. We don't know if we're at equilibrium. Q and K only include gases and aqueous solutions. So remember, no solids or liquids are ever given in any K or Q expression. Solids and liquids are never in K or Q expressions. Now, similar reactions will have similar K values at the same temperature. Biggest thing with equilibrium constants, pay attention to what K it wants. Kc means you have to have brackets for concentration. Kp means you have to have pressure. If they ask for Kp and you give concentration, you give brackets, they will not give you the points for that expression. So just pay attention to what K you are working with. Notice how the exponents are just the coefficients from the balanced equation. So just make sure you're paying attention to which K is being referenced. Topic 4 focuses on calculating K. Topic 4 looks at calculating K. So equilibrium constants can be determined using concentrations of reactants and products at equilibrium. If we are calculating K, it has to be at equilibrium. Now, if we want to just calculate the equilibrium constant, we plug in the equilibrium values that they give us into the K expression. So here are the steps for solving for K. Always, always, always write an equilibrium expression. So either Kc, Kp, maybe that's Ksp, but always write your equilibrium expression. You know it's equilibrium if you see a double arrow. Then look at your molar concentrations or your partial pressures, and then plug it into the K. So in order to solve for K, they have to be at equilibrium. If you're plugging in values that they give you, that means you're calculating Q, not K. So topic 4 is how we can calculate the equilibrium constant, not concentrations. We'll look at concentrations in a separate topic. Topic 5 focuses on the magnitude of K. Magnitude means the value. So if you see a question that says, what is the magnitude? It's asking for the value. So this looks at the magnitude of K. What does the size of K mean? Well, a lot of times we see K values being either very large or very small. If K is very large, think about the expression, products over reactants. If K is large, products are favored. Forward reaction is favored, reactants turning to products. We see K being very small. Well, that means that we have more reactants compared to products. So we would say that favors the reverse reaction, products converting to reactants. Now I added this bullet point in here because we actually saw a free response question a few years ago where it gave a ridiculously large K value. Very, very large K value. If you see a K value that is extremely large, times 10 to the 30, that actually proceeds to completion. If we see a very, very large K, we just treat it like a stoichiometry problem. It's no longer equilibrium. We assume all of our reactants convert to products. Now, the size of K can be used to look at what we have more of, more reactants or more products. So remember, when we have a small value of K, we have mostly reactants. A large value of K, we have mostly products. And if it's somewhere in between, we're going to have similar amounts of reactants and products. But remember, this focuses on 1, right? If we're greater than 1, we have more products. If we're less than 1, we have more reactants. Just like rate constant, equilibrium constant is a positive number. That's because the equilibrium constant is derived from the rate constant. Your K's have to be positive. All of your K's, your rate constant and your equilibrium constant, they have to be positive numbers. They can be tiny numbers, but they need to be positive numbers. Now, topic 6 focuses on properties of the equilibrium constant. So what happens if we flip a reaction? What happens if we multiply a reaction? What happens if we add 2 reactions together? So this is thinking about Hess's law. If we have a reaction, reactants are at equilibrium with products. We have a certain K. Right? Our Kc is products over reactants. Now, what if we run the reaction in reverse? What if we flip this? Well, now it becomes pressure to reactants. Well, now Kc, because it's still products over reactants, now it's R over P. Notice what happened to the Kc. They flipped. But flipping an equilibrium constant is not changing the sign because K cannot be negative. When we say flip, we're flipping the fraction. So if we flip a reaction, we take the inverse. If we multiply by a constant, so if I multiply this by 2, now it's 2R and 2P. Well, remember, we don't put the coefficients out front in a K expression. They become exponents. So if I multiply this reaction by 2, I'm adding squared to both of these. So I'm squaring K. So if you multiply a reaction by a constant, you're going to raise the equilibrium constant to that power. And if you add two reactions together, you actually multiply the equilibrium constants. So you have to remember that K is a little bit different than when we did delta H or delta G and we were adding reactions together. So that's what topic 6 is all about, how K changes. And since Q and K are calculated in the same manner, if we were manipulating Q expressions, it would be the same thing. So then topic 7, this is calculating equilibrium concentrations. So instead of an equilibrium constant, now we're looking at concentrations. Well, this is a little bit different than when we were just calculating the constant. Equilibrium concentrations are calculated using the value of K. And then typically, if we're calculating equilibrium concentrations, they probably are going to give us initial. Well, our steps to solving equilibrium concentrations. Again, always write your equilibrium expression, your Kc, or your Kp expression. If you have something at equilibrium and you are not sure where to go, set up an ice table. You have something at equilibrium and you're not sure where to go, set up an ice table. Some people call it RICE, R-I-C-E, because that R reminds you to have a reaction. So ice, initial change, concentrate, or initial change equilibrium. And so if you set up an ice table, fill in initial amounts. Remember, ice table has to be moles or pressure because it's Kc or Kp. Our changes, if we don't know what the change is, they give us nothing about equilibrium, then we use X's. That's where then we do initial and the change equals equilibrium. So maybe we have 0.1 plus X or 0.1 plus 2X. Remember with the change, look at the stoich. Look at the coefficients, because if it's 2H2, then it would be plus 2X for the change. Reactants get used up, so that's minus. Products get created, that's plus. Then we can actually solve using the K expression. Now, do you remember what we could do to prevent using the quadratic? Assume X is small. So to prevent using the quadratic, you just have to make yourself a note. Assume X is small. You never need to use the quadratic formula on a free response question. If it looks like you have to use quadratic, assume X is small. So you're assuming that subtracting X from something will not make a difference. And then you can do the algebra using the X's, using the K, and you can solve for X and plug it back into your ice table. So if you're in doubt and you see something at equilibrium, you see a reaction with a double arrow, set up an ice table. Topic 8 focuses on representations of equilibrium. So we looked at some of the graphs in topic 1. This is actually a multiple choice question that I just took the picture from. And for this, it gave us a particle diagram, and it asked about when equilibrium was established, or if equilibrium was established. If they give you particle diagrams, it's the same thing I say every time you see particle diagrams. Count your particles. Count the different number of particles. We know that it's reached equilibrium once the concentrations remain constant. So I notice at 200 seconds, I have 3 XY molecules. I notice here I have 1, 2, 3, 4, 5 XY molecules. 1, 2, 3, 4, 5 XY molecules. So I noticed that at 300 seconds from then on, concentrations remain constant. That tells us we've reached equilibrium. If they just gave us one snapshot, so they just gave us this 200 seconds particle diagram and they said, is it at equilibrium? Well, we don't know. We need more than one time frame to see if something is at equilibrium. So this is just looking at, can we determine if equilibrium has been reached based on particle diagrams? And we need to see multiple times in order to see that. Topic 9 looks at Le Chatelier's principle. So if you remember, we talked about Le Chatelier's principle being what happens if we have a system at equilibrium and then we make a change. So a system has to be at equilibrium first in order for us to use Le Chatelier's principle. So there are 3 main factors that can cause a shift in a system that's at equilibrium. We change concentration, we change pressure, or we change temperature. And what I did on here, again, this was unit 6 for us. So if you want to go back, you filled a table just like this in your unit 6 notes. But this is looking at all of the different changes and how the reaction will shift to reestablish equilibrium. We're going to look at some pre-response questions. We have to be careful how we talk about Le Chatelier's principle now. And we'll look at it in the next topic, in topic 10, because they have us tie it into Q now. So if we make a change, what you need to think about. Remember when we did Le Chatelier's principle, we talked about the seesaw, right? You make a change, you add something, well, now it's no longer at equilibrium. So you have to think about which way does it have to shift to get back to equilibrium? And that's what this is looking at. Remember pressure. Please pay attention to pressure. Or when you change volume, because volume changes pressure. That only affects gases. Notice how it says shifts toward less gas molecules. Not less molecules in general, but less gas molecules. Adding an inert gas, that's not in the K expression, that's not going to affect anything. The only thing that affects K, the equilibrium constant, is temperature. Nothing else affects equilibrium constant except for temperature. Just like nothing affects rate constant except for temperature. And so what I'm going to do is I'm going to actually look at one more slide because part of the unit guide actually says to focus on dilutions. So part of topic 9 says to know how a change will be made based on a dilution. So when something is already at equilibrium and we change the concentration, if we increase the concentration, right, the system is going to shift in a way to use up what we just added. Concentration is decreased. Well, now we don't have enough. The system is going to react to produce what we just took away. When a solution is diluted, a dilution means you lower the concentration. So if it says that something is diluted, you are decreasing the concentration of that substance. So the reaction is going to shift to increase whatever was diluted. So they've started adding in just a couple extra new things. This was one of them. Dilutions change the concentration. When you dilute something, you are lowering the concentration. I have to dilute acids for us to use in lab, because otherwise it's too high of a concentration. I dilute it down so it's a lower concentration. So just keep in mind, if something is undergoing dilution, you're decreasing the concentration. This is just looking at Le Chatelier's principle experimentally. Keep in mind that we can use Le Chatelier's principle if they give us information like color. So we've seen this in multiple choice questions before, where the reactants are pink, the products are blue, And it says, well, if we notice that something is pink, what was done to the system? It's just having you apply and say, okay, well, if the reactants are pink, what do I have to do to the system to push the reaction to create more reactants? Or maybe it's yellow and orange. And we say, okay, well, if it's yellow, we're pushing to the reactants. If it's orange, we're making more products. So just being able to apply colors as well if they give us a system that has colors. Topic 10 is Q versus K. So remember, Q is at any point in a reaction. Q helps us determine which direction the reaction has to proceed to get to equilibrium. Q, we are not at equilibrium. K is at equilibrium. That is the equilibrium constant. So we have Q less than K, greater than K, or equal to K. And so I saw this when I was looking at an AP review where you write K and then Q. And it was pretty clever because based on how K compares to Q, it shows the arrow. It's the same thing that I do with, so here, like Q is less than K. So remember I did Q less than K. The size of the bar is less than K. So when Q is less than K, the reaction proceeds from left to right. So reactants create more products in order to achieve equilibrium. Because if Q is less than K, that means we don't have enough products. If Q is greater than K, right now Q is too big. Q is what changes to get to equilibrium. So if Q is too big, we need products to create more reactants to achieve equilibrium. Once Q equals K, system is at equilibrium. AP wants us to use the Q versus K reasoning for pretty much everything now. If it says use Q, make sure you're talking about Q. We don't see Le Chatelier's principle actually being used as much anymore. So this was exactly what I just gave, that table with Le Chatelier's principle, except now this looks at the effect on Q or K. So I just added a third column to that Le Chatelier's principle table. So if it says, how does adding a reactant affect equilibrium, use Q versus K. Well, if it says use Q versus K, you can't just say, well, we added a reactant, it shifts to the products. You have to talk about Q. Well, when we add a reactant, we're adding into the denominator of Q, which is making Q smaller. So Q is smaller than K. The reaction needs to shift toward the products to increase Q to equal K. So then again, temperature does not affect Q. Temperature affects K. Here's how K and temperature are related. It depends on if the reaction is exothermic or endothermic. So I added this into topic 10 because this is looking at Q. You could also tie this into Le Chatelier's principle. But it depends on if the reaction is exothermic or endothermic. Remember, when the reaction is endothermic, heat goes into the system. So heat acts as a reactant. And so since heat acts as a reactant, if you increase temperature, you're adding heat. Now we have too much on the reactant side. So the reaction is going to shift to make more products. Well, as it makes more products, now you have more products compared to reactants. So K increases. Decreasing temperature, now you don't have enough heat. The reaction will shift toward the reactants. K decreases. So changing temperature changes K. But the way that K changes is based on whether the reaction is exothermic or endothermic. That's why when we were looking at these problems and it said delta H was less than 0, meaning it's exothermic, we added heat to the product side. Changing temperature does not change Q, it actually changes K. So now we'll go through topics 11, 12, and 13. This is KSP. So topic 11 is KSP and solubility. So K, again, it's just another type of equilibrium. SP means solubility product. KSP focuses on a solid at equilibrium with its ions. So we have a solid at equilibrium with its ions. That's KSP. Now, if KSP is greater than 1, we would have that solid, that salt, as soluble. If KSP is greater than 1, we would consider a salt soluble, meaning it dissolves in water. Most of the solids that we look at have a very small KSP, which means that they do not dissolve easily. Here are some examples of KSP expressions. Remember, we have a solid at equilibrium with its ions. Now, technically, we have plus H2O in all of these because this is barium sulfate dissolved in water, magnesium hydroxide dissolved in water. We just ignore the water part and we just look at the solid at equilibrium with its ions. So if it says write the equilibrium reaction of calcium fluoride dissolved in water, well, we're just putting a solid into water, breaking it up into its ions. But it's going to be at equilibrium because it's not potassium nitrate, ammonium, or sodium. KSP expressions. Why do they only contain the products? Why aren't there reactants?
Those are solids.
They're solids. So you still, again, no solids, no liquids. So it's just the products for KSP expressions. So this is looking at an example of calculating solubility. KSP was the second half of our chapter 8. So when you're given KSP values, a lot of people just want to compare the KSP values and say, oh, well, this is a larger KSP, it's more soluble. But they are not the same thing. You can only compare KSP directly for solubility if the ratio of ions are the same. In this case, the ratio of ions are not the same. Right here we have MnCO3 at equilibrium with Mn2 plus and CO3 2 minus. Here we have manganese hydroxide at equilibrium with Mn2 plus and 2OH minus. Well, it's 1 to 1 and 1 to 2 in the other. So we have to actually calculate solubility. So what we'll do is we'll actually look at how we can calculate solubility. Remember we used an S when we were calculating solubility. So, all right, so it reminded us what we were actually looking at. We are going to, this is kind of one example that I want to do. I want to review solubility and calculating solubility. So I have the equilibrium reactions written. And remember when we calculate solubility, really we're just focused on the equilibrium amounts. So the solubility is the number of moles per liter of solid that dissolves. And so if we have S amount of MnCO3 dissolve, we also have S amount of Mn2 plus and S amount of CO3 2 minus. And so if we plug that into the KSP expression, KSP is just going to be Mn2 plus concentration times CO3 2 minus concentration because solids aren't included. Well, here's our KSP expression. 2.3 times 10 to the negative 11th equals S times S. We take the square root, we find the solubility. Now, if we look down here, so instead of putting a line through, I'll use S for MnOH2. Pay attention to the ratios. Well, that means we have S amount of Mn2 plus, but we have 2 times that for OH minus. So if I write the KSP expression, this is why we can't just use KSP if the ratios are different, because we have the concentration of Mn2 plus times the concentration of OH minus, but don't forget about exponents. Concentration of OH minus squared. Now, if we plug in our information, KSP was given to us up here. 1.9 times 10 to the negative 13 is S times 2S squared. What is quantity 2S squared? 4S squared, right? So 4S squared times S is 4S cubed. And so because the ratios are different, solving for solubility is also different. So solubility and KSP are related to each other, but they are not the same thing. If you need to review calculating solubility more, again, this was the second half of Unit 8 in our notes. So going along with solubility is the common ion effect. And we looked at the common ion effect when we looked at acids and bases as well for Le Chatelier's principle. And then we tied in acids and bases. So the common ion effect is nothing more than an application of Le Chatelier's principle. So the solubility of a salt can be decreased when we add a common ion. So here's an example down here. We have barium sulfate solid at equilibrium with its ions. KSP and solubility. If we're looking at solubility, typically we're looking at the solubility in pure water. However, if we add Na2SO4, we're adding SO4 2-. Think about Le Chatelier's principle. Now you have more product. The reaction is going to shift back toward the reactants. The less ions you have, the less soluble that solid is. So the solubility of a solid is reduced when we add a common ion because it shifts the equilibrium back toward the products. Topic 13 goes along with solubility, and it looks at the pH with solubility. If an ionic solid is more soluble in an acidic solution, so if an ionic solid is more soluble in an acidic solution, that means that its anion is a weak base. So if an ionic solid like calcium fluoride, CaF2, that is more soluble in an acid because F- is a weak base. Weak bases react with acids. And so what happens when you add an acid, the value of the anion will decrease. And so since you're using up, so for example, if we have calcium fluoride and we add an acid, the F- ions are going to react with the H+. So that's decreasing the amount of product of the original solubility. It's decreasing the amount of F-. So the reaction needs to shift to make more F-. That means that more solid is going to dissolve to create more F-. So we can also affect solubility by thinking about how the cation or the anion will react with something added. And this slide shows the same thing. It's actually showing step by step for magnesium hydroxide. And it shows another example in terms of particle diagrams. So it's showing the exact same thing with adding an acid to something that has a basic anion. OH- is a base. We add acid, we're removing some of the OH-. Well, now if we remove some of the OH-, magnesium hydroxide, it's going to dissolve more to make more OH-. And so the more the solid dissolves, the more soluble it is. And so the last slide just shows general examples. Biggest thing on this is showing qualitative analysis. It's different lab examples looking at, we could pull out different ions. This used to be a lab that was done, not as much anymore. But this is the biggest thing. The lower the KSP, if we are in lab, the lower the KSP, the less soluble the substance. So the lower the KSP, the more likely it is to stay as a solid. If the ratios of ions are the same, we can just use KSP to rank solubility. So the lower the KSP, the less soluble the substance. The higher the KSP, the more soluble the substance. Just think about the equilibrium constant expression.